Hello everyone, my name is Moises Gilberto Zarzosa Medina and I am a part of the Applied Nanomagnetism Group at the Instituto Regional de Investigación Científica Aplicada de la Universidad de Castilla-La Mancha in Spain. Today I will talk about our work on the gas phase synthesis and magnetism of palladium iron oxide core shell nanoparticles. Palladium-based nanomaterials have attracted considerable interest because of their excellent ability to absorb hydrogen. By allowing palladium with a magnetic element such as iron, we may obtain single-phase ferromagnetic nanomaterials that keep hydrogen sensitivity while introducing magnetic functionalities. For example, palladium-rich palladium-iron alloy nanoparticles could combine the hydrogen detection and catalytic capabilities of palladium with magnetic properties such as magnetoresistance, which have been studied in bulk palladium iron. However, the magnetism of palladium iron nanoparticles is much less understood than in bulk materials. One important factor is the possible formation of core shell architectures due to iron surface segregation and iron oxide shell formation, which can strongly influence the magnetic response. Gas phase synthesis methods like magnetron sputtering allow the fabrication of quasi-percolated nanoparticle films with controlled composition and potentially enhanced sensitivity. In this work, we use such a method to fabricate iron palladium-based nanoparticle films and investigate their structural and magnetic properties. Our hypothesis is that palladium iron nanoparticles synthesized via gas-phase magnetron sputtering form core shell structures consisting of palladium iron alloy core and an iron oxide shell. This can occur due to differential diffusion, also known as Kirkendall effects. We expect that this architecture, together with the intrinsic ferromagnetism of palladium iron alloys and the magnetic properties of the iron oxide shell, we produce nanoparticles with enhanced and tunable magnetic moments. To produce these nanoparticles, we use a composite target made from a 2-inch pure palladium disc with a variable number of iron pieces mounted on it, as the figure 1. The deposition was carried out by DC magnetron sputtering at a base pressure of 10 to the minus 6 millibar and an argon pressure of 10 to the minus 3 millibar. We test 3 different DC powers, 60, 90, and 120 watts to control the iron amount on our nanoparticles. We measure the deposition rate and thus the total nanoparticle mass per sample using a quartz crystal microbalance. The resulting nanoparticles had an average diameter of about 4 nanometers and were deposited as thick quasi-percolated films on small silicon substrates of 5 by 5 millimeters. For our results and discussion, we characterize the structure of nanoparticles using high-resolution TEM anneals. In specific, for our sample with 14% of iron content, we measured a mean diameter size of 4.1 nanometers, and the images suggest that a palladium-rich core surrounded by a shell of iron, which is consistent with the core shell structure. We then perform XPS measurements at the palladium 3D and iron 2P edges. In uncapped nanoparticles, increasing the iron content did not cause a significant shift in the palladium 3D peak. This suggests that the iron may diffuse to the surface, so only a small amount of iron could be alloyed into the palladium core. And when we cap the nanoparticles with niobium, which also serve as a matrix to prevent oxidation and iron diffusion, the results were different. For low content of iron, for low content, we refers to below the same resolution, 1% at most as compared with palladium. We saw a small peak shift, indicating that a iron palladium alloy is present even at very small iron concentrations. For higher iron content, for our case around 20% of iron, more iron was incorporated into the core and the alloying effect was stronger, so we saw a larger shift in the palladium peak. The iron 2P spectra show that in uncapped nanoparticles, oxidized iron phases appear regardless the iron content and the metallic iron peak is absent. This tells us that oxidation happens when the nanoparticles are exposed to air, and probably that diffusion to the surface is promoted by the presence of oxygen. Now let's look at the magnetic characterization. First, the magnetization curves show that the saturation magnetization depends on the iron content. This can be explained by the combination of polymagnetism from the palladium core and the Erkaka-White type hybridization effects, where iron promotes the polarization of palladium conduction electrons. Next, we perform exchange bias measurements at 5 Kelvin after cooling in a 3 Tesla field. The absence of exchange bias in all samples supports the palladium iron oxide core shell model. Typically, exchange bias appears when two magnetic phases with different anisotropies are exchange coupled below the ordering temperature of the harder phase. If the core and the shell in our nanoparticles were strongly coupled in that way, we could expect a shift in the hysteresis loop, but we don't not see that in this case in our study. We also measure the AC magnetic susceptibility with a small field amplitude at different frequencies. The peak in the real part of the susceptibility shifts with frequency, which is a hallmark of spin glass systems. And finally, from the Arrhenius plot of the freezing temperature, in our case T sub F, versus frequency, we extract the critical exponent indicating that our systems behaves as a frustrated ferromagnets. So in summary, gas phase magnetron sputtering allow us to synthesize palladium iron nanoparticles. Instead of the expected homogeneous alloy, we obtain palladium iron oxide core shell structure caused by the iron segregation and oxidation. Structural and spectroscopic analysis confirm the presence of palladium-rich core and an amorphous iron oxide shell. The magnetic measurements reveal a combination of soft ferromagnetism and spin glass behavior consistent with the disordered shell. And the absence of exchange bias supports the proposed architecture, and the high magnetic moment of iron, or the change of magnetization as a function of iron, suggests a strong polarization of palladium through Erkaka-White type interactions. These findings give us new insights into the interplay between structure and magnetism in the dilute palladium ion system, and they open the way to tailoring multifunctional nanostructure for hydrogen sensing and spectrometry application. Thank you for your attention.